Hello, MTI members. This is Tom Morrison right here beaming in to you from the Metal Treaty Institute home office in Jacksonville, Florida. We're all MTI strong today and hope you are. Today we're going to be talking about additive manufacturing, otherwise known as 3D printing. And I know a lot of you are wondering, how do they print those nuts and bolts from a big laser printer? Well, I'm here to tell you they do not do that. They do it in a much different fashion. We've got a seasoned expert here, Bob Hill from Solar Atmosphere. Bob, say hi, everybody.
Hello, everybody. Good afternoon.
So I'm seeing on the chat line over there, everybody's chiming in. That is a place on your right-hand side. You can go to the bottom. Anything you hear, if you want to ask a comment or share a comment on 3D printing or what's going on, or ask comments from everybody, you can just go to the right there and you can ask a question or post your comment there for us to address. But very excited to be here today. 3D printing is really a game changer in manufacturing in all industries, and it's imperative that everybody on this broadcast be looking into it and researching it. And we're excited to have Bob here to tell us about really how it's going on in the aerospace and vacuum industry, but it's really seeping in to a whole lot of industries past that. So Bob, I'd like to ask you, for those that are online and have never met you before, tell us who Bob Hill is.
Okay, Tom. Good afternoon again. My name's Bob Hill. I'm president of Solar Atmospheres of Western Pennsylvania, located in beautiful Hermitage, Pennsylvania. Unfortunately, right before we came on the air, I'm a little harried. I apologize. If you look over my shoulder, you can see a dark hallway. We lost power here. So unfortunately, with all the technology we're going to be talking about today, unfortunately, our whole plant is out of power right now. In fact, the whole town of Hermitage is without power. So.
Well, Bob, the MTI signal is strong today.
Yeah, so if the power does come on, I'm working on generator power right now. If there is a blip, I will dial right back in again, but hopefully this will go smoothly, Tom. Hopefully we'll get power real soon. Thank you.
Great. So Bob, as you look at 3D printing, this has been something that's been evolving over the past few years. Why has Solar dived into 3D printing and doing some stuff in it?
Actually, Tom, the technology is rather old. It started really in the 1980s. And just like any kind of technology, transformative technology, it takes a while to build a popularity and to gain acceptance. So unless you've been living under a rock for the last 10 years, everybody I believe on this call knows what 3D printing or additive manufacturing is. Basically, it's a manufacturing process where a digital model is converted into a component or a part, layer by layer, versus subtracting material from a billet or a bar or a plate in typical traditional metallurgy. So it's a totally different beast. It's versus machining, and I was not a big proponent. I'm not, by the way, Tom, I'm not an expert in additive manufacturing by any means. I am getting more and more additive manufactured parts in the plant every week, more than ever. So if you would have asked me this a year ago, I would have been very skeptical. But today, I believe it's more than just hype. It's a reality. So I have seen what's going on with additive manufacturing, and it is here.
So you alluded to what 3D printing is. I mean, so how does it build a part from the ground up? So
there's basically what I have learned, Tom, from my customers, basically 3 different ways to print a component. And I went in the shop today and I actually found 3 examples to show the audience of the 3 different methods of printing. The first method is known as the direct metal laser sinter process, or the DMLS process. And I have a block here that I wanted to show everybody. I hope you can see that. Basically, you can see the basic DNA of any printed part. You will see it's printed on a base plate, and the component is built up from the base plate. So all printed parts start with a building block or a base plate. And the way we've been getting these parts in, and I'm sure everybody else on this phone call has been getting parts in, you get them already attached to the base plate. And then later, after heat treatment, they EDM or saw off the component off the base plate. And they like to make these base plates nice and thick. This base plate is about an inch and a half thick, which is too thick actually. But they like using a thick base plate so they can reuse that base plate once more and more every time they go to print a component.
Right.
But here you see a DMLS process, and basically the DMLS process is within an inert chamber. Laser melts powder. There's powder deposited layer by layer onto the target material, forming a pool of molten metal. The metal powder is then delivered into the molten metal pool, forming a deposit. And then the platform lowers, and then the next layer is printed. So you basically print these columns. And I'm sorry, this part is not too sexy, but it's very, very expensive material. These columns are made of Invar 49. If you know what the cost of Invar is, very, very expensive. So I assume this customer wants to print this very expensive material so they have no waste or chips made from machining out of a big Invar bar or plate. So this is one example of a DMLS. And I must admit, this process is taking over on a lot of the kind of work that we see every day. The DMLS process has a very low rate of deposition. However, you can make real fine details. I don't have an example today, but I can give you examples of cavities that are printed that could never be machined, or bosses that are on certain critical areas that could never be machined. So it can be very, very fine in detail with the DMLS process.
So Bob, I got a quick question for you. So that particular piece, by doing it 3D printing, did it change how and the amount of heat treating that you would do on that particular part?
It changed. Yes, it's a totally different heat treatment than we would normally do on Invar material. Mm-hmm. Invar material, we usually do a very low temperature, stress relieving, because Invar is usually used for outer space materials, satellites, and they want less expansion contraction in the outer space atmospheres. So yes, it's a totally different. I can't divulge the kind of heat treatment we're doing to that part because it's all proprietary. By the way, a lot of these things all come with NDAs too, so I can't really talk a lot about the heat treatments, but it's a totally different heat treatment because basically what you want on that part is full density. Right. You're looking for full density of the product. So with wrought product, you already have full density.
So on a piece like that, I think the big thing people are thinking is you heat treated it one way before, and now 3D printing and additive manufacturing comes along, and now you heat treat it in a different way. So when you look at the overall business prospect and application, would you say, we can't talk pricing and that stuff, but I think the big question is, well, so did that create more opportunity, or did it actually create maybe less heat treating, having to change the process?
I think that's still to be seen, Tom. It's
okay.
Still rather new. One thing I believe, the pricing on parts, instead of pricing per pound the way normal heat treaters do on bars and billets and ingots, I think it might be priced per an each piece going forward. Right. As a component, as a finished part more. I don't know. I don't know the answer to that. So far, I have actually seen a few more heat treating cycles with AM parts than with traditional metallurgy, but right. Still too early to tell.
Right. Well, and I think it's a little early to tell if they will ever be able to 3D print the perfect part that needs no heat treating. I don't think we've seen that yet, but I think that's the biggest fear from a lot of people is as they really play with the molecular structures that they could maybe create the metal that it doesn't really have to be heat treated.
Well, I'll go into that also a little bit later in the talk.
You have two more parts too?
That's a big threat.
Okay.
So the second way of printing that we have seen here at Solar, and I'm sure everybody else out there has seen, is what's known as the EBAM process, electron beam arc melting. And the difference with this process, and I have a sample here of I can lift this up. I'm sorry, this is titanium. The other thing's really heavy, but titanium is very light and strong. As you can see, this is the buildup of titanium weld per layer to form this shape. And the EBAM process is again done in an inert atmosphere under argon. It uses a multi-watt electron beam to selectively fuse the wire onto, again, a backer plate. You can see the backer plate once again. In fact, you can see this backer plate's real. I don't know if you can see it, but if I put a straight edge to that, it's really warped because of this buildup. It bends the plate. So that adds another heat treatment for us to stress relieve that backer plate flat, so that forging or that part is nice and flat when they do excise it off the backer plate. And multiple layers of wire are laid down, and it really gives you a high rate of deposit. So this is a very fast rate way to print shapes. It's very rough, though. As you can see, it's not as detailed. It's a rough shape. In fact, Tom has a copy of our, I just ran across this ad in Aviation Weekly. And Tom, if you could show that ad to the folks. This ad, this is for the customer. The customer is North Titanium. And if you see in that bottom corner, that's the finished product of this part. And as you can see, this is going in the 787 Dreamliner, and it's an FAA approved 3D printed structural component. That's the first one that I know that's structural that will be flying in the aircraft. And we were very instrumental in getting this part to full density and to get it qualified for flying in the aircraft. That's called the electron beam arc method. And we've seen a lot of this basically because it's a very fast process. It prints shapes very quickly. Alcoa or Arconic also just added on what's known as they add a forge operation to this, where they can actually forge a shape, which eliminates the inclusions and the porosity in the build. So that's another new facet that Arconic added to this type of printing. And then the third type of printing that I want to mention, I didn't really have a part here. It's not as popular as it once was, is the binder jet process. And this is much like your printer in your office. And I just have this nameplate. It's actually our sales manager, Michael Johnson. But as you can see, the nameplate itself is the backer plate, and they build up and they sinter powder layer upon layer with low heat, very low heat, to build up this shape. And the same thickness of the border of the plate as the name Michael Johnson. And then they just take a grind and they just surface it off, so the name comes out very clearly. But what I wanted to show everybody, you cannot machine something like this. The 3D printing of these cubes of different heights within that nameplate, you cannot possibly machine. So this is just an example. It's a decorative piece. That's all it is. But this is the binder jet process. Again, some of the problem, this is the lowest cost method that we have discovered. The deposition is very slow. However, details can be very fine. And one thing that we have to worry about this process in the vacuum furnaces that I want everybody to be aware of versus the other two processes, they use a binder in this process. And the binder can hurt your vacuum furnace if it's not properly delubed. So the binder jet process, you have to be a little bit more wary of the process. The temperatures used for sintering this material, it's just like the MIM process, right? So this part it doesn't travel well. It comes like a piece of wet sand, a little bit stronger than that. But when you do the sintering process, then you have fully dense part. And you have to worry about the binder that's in that material. So there are the three main processes, Tom, that we have discovered. There might be more. I'm sure other people in the audience, maybe they have more, but these are what we have seen so far, and we're seeing on a daily basis.
So you know, Bob, when I see the nameplate, now it makes me think of, just as an example, the type of threat that exists in certain industry. You think about the sign industry. you just held up a nameplate that you could print right in, if you had the printer in your office. And if a lot of people had those printers in their offices, your local sign shop would now not be doing those nameplates for many people. So the sign industry has a direct threat when it comes to parts of their revenue streams going down and not knowing it, because you can now maybe print your nameplates right in your office or your little small sign. So I use that as an example as why people need to study this stuff, because little things like that, the sign industry may or may not know, especially the smaller sign guys or ladies may not know that that's going on. And it could totally wipe out a certain section of your revenues and you not know about it.
Right, Tom. And to sharpen that sword a little bit further, what we're interested in as heat treaters is how this part, not so much how the aircraft looks, but why is that structurally sound in an aircraft that allows that aircraft to fly high and fast. And that's what we're interested in as metallurgists. What is going on with this process? Yeah, you can print full-size cars, you can print anything you ever want with any materials, but how microstructurally is that going to be viable for mechanical properties? And that's the big key for us.
Well, and I think even when we'll get deeper into some other industries that are involved in that, but when you look at, so you talked about 3 different parts. So what about printing methods being used to print the components as far as heat treating? Have you addressed any of that at all?
The printing processes?
Are there any different printing methods being used to print the components? Or are those the 3 that you, is those the only 3 that you talked about?
The DMLS, the EBAM process, electron beam, and the binder jet process. They're the 3 processes that I know of that we have heat treated parts to.
So before we get into how 3D printing is changing manufacturing, what do you think opportunities there are for the heat treaters out there trying to look and say, where do we fit into this process?
Well, I think there's a lot of opportunities, Tom. Number one, I sincerely believe vacuum furnaces are the way to go with additive manufacturing. And I think that's why the AM companies are coming to us at Solar, is because we have a lot of vacuum furnaces all over the country. So the vacuum furnace is a must for additive manufacturing. Why? The vacuum furnace, you know, this whole process defines near net shaping. They want finished shapes. So with a vacuum furnace, you will not oxidize surfaces. You will not have introduce grain oxidation. So additive manufacturing, in my opinion, is made for the vacuum furnace. The temperature control is very critical. And vacuum furnaces, as you know, some of these temperatures, we have to hold plus or minus 2 degrees Fahrenheit. And we can only do that with a vacuum furnace with the way we're able to thermocouple internally and externally on the part. By the way, you know, thermocoupling a base plate on something like this, you could drill holes in this, and that's not necessarily what you really want to test. You will really want to thermocouple the actual part. So we ask our customers, this is a scrap part, to actually drill this part so we can put thermocouples so we can see the thermocouple profile of the component being heat treated. We don't care to know what the temperature of the base plate is.
Right.
So the temperature is very important. Sintering temperatures on some of these can reach as high as 2,500 degrees Fahrenheit. And that lends itself very well to the vacuum furnace. Vacuum furnace technology also allows for hydrogen partial pressures on that binder jet process. Sometimes they request flowing hydrogen, and that helps with the mechanical properties of that part. We can also utilize slower ramp rates and utilize hold points with the vacuum furnace very nicely for delubing, like I mentioned in the binder jet process. Also, graphite fixturings are used quite extensively in the vacuum furnace for AM. We use it quite a bit. When we have a piece this big, that's as big as a wing of an aircraft, that base plate is really warped up, so we can put a lot of weight on that titanium plate and lay it down or creep flatten it to using graphite, where you can't use graphite in air or atmosphere furnaces. Also, we have learned the hard way that these kind of materials that we're dealing with, titanium, zirconium, very, very expensive materials, they require at least 10 to the -6 torr ranges or deep into the 5 scale. So the very, very deep vacuum levels are needed for a vacuum furnace. That, I think, Tom, is why they're coming to us as the experts, and others on this call as the experts in the heat treating realm. So that is why we're getting the calls.
Well, you mentioned one thing. You said lesson learned. Is there any other further lessons learned? I mean, you're in the beginning stages of this, of where it's going to actually be in a few years. But any lessons learned as you've gone through this process the last couple of years about heat treating the parts or dealing with the manufacturers and talking about the parts?
Yes. We over the past year, we've had a lot of instances of lessons learned. I already mentioned having a thick plate like this is not good. A thick base plate like that on these small parts that are printed is not good, because you have a different coefficient of expansion of the base plate versus the printed component. Now, these are blocks, it won't matter, but we've run real thick base plates like this because the customer wants to use the base plate over and over again, and they print real thin cross-sectional parts with cavities, and the cavities have blown out, have cracked. There's been superficial cracks at the base of the component. So when they went to cut the part off, the part was essentially no good because it was cracked. So the more you can match the base plate to the thickest cross-section of the printed component, it's very critical. Also, we're always trying to educate the printing engineer not to print something out of 4140 where you have to oil quench it, or 4130 material or carbon steel. You want to use something, if you want to harden it, you want to use something that's air hardenable. Again, for vacuum furnaces. The whole reason for this process is to minimize distortion and to keep the shape at the nearest net shape as you can possibly keep it. So we have learned that way. Also, we have also advised printing engineers that from now on, they can print any profile that you ever want. Anything you can put down on paper, right? They can print. Well, print us thermocouple holes. So we can, in their actual part, that we can actually thermocouple their part. Don't have me drill it, print it. And therefore, you give us a scrap part that we can use as a thermocouple hole to give a good profile of what's going on thermally with that component.
Now, you had mentioned a few seconds ago the thickness of the faceplate to the thickness of the part. Is that an area where a heat treater can be a great expertise and resource for? I mean, are they printing them on thick plates because they just don't know any better, or?
Yeah, like I said, Tom, they're printing them on thick plates because they're cheap. They want to use them again and again and again. Well, that's not good for the component, because we're going through heating and cooling cycles that cause some very, very difficult stresses in that area, and it's not good for the printed component. So they're doing it to save costs, but we're telling them not to cut corners on it like that.
Right. So any other lessons learned that, I mean, like what's the biggest one you would say, if you could say one thing to everybody online that's looking at tuning in to 3D printing, additive manufacturing, what's one thing you would say, if you're going to remember one thing, remember this lesson?
Well, I would ask a lot of questions on how the part was printed. Exactly what I mentioned. Binder jet process, be careful. If you have a part that's printed at a binder jet, you know the part is going to be very, very fragile. It's going to be just like a metal injection molded part. It doesn't travel well. Coming to your plant, you might open up the box and you might see crumbles of parts broken apart because it's not fully densified. And when you go to run that part, be careful, because the binders could ruin your pumps and your vacuum furnace. So you have to ask a lot of questions. If they were properly delubed before arriving, there's no worry about that with the DMLS process or the EBAM process. There's no contaminants. That they are very, very clean. The other thing that I should let you know, also with all three processes, that hipping is really, really necessary with a lot of these companies after our processing in the heat treating. So those companies out there that are involved with hipping, you might get a double bang of processing, because most of these parts that are printed do require hipping. And what hipping is, Tom, it high isostatic pressing, and that makes the structure much more homogeneous. If there's a void or a void in that microstructure that could cause a possible failure, what hipping does, it closes those voids and it makes a more homogeneous structure.
Right.
So hot isostatic pressing is a very, very important process going forward in this, and something that we have to all look at. Now, we have one customer that avoids the hipping, and they do a 100% CT imaging of all the parts. So either an X-ray image or hipping as a final assurance that you have a good quality 100% dense part is most critical. So I would think they are the most critical features. Again, what I just mentioned about having thermocouple hulls, having them choose the right kind of materials, using a vacuum furnace, that's all important.
So when you look at, now let's shift from specific to 3D printing to the business of 3D printing and a manufacturing process. From what you've seen in 3D printing and additive manufacturing, how do you think it could change manufacturing overall?
Well, I think definitely going to be less input material, which means less waste.
Mm-hmm.
There are going to be zero design constraints now. If you can put it on paper and you can print it, you cannot machine all those features, but you can print it. We have jobs in here where they've actually printed little bosses on typical traditional metallurgy. We have internal cavities. We even have done some work with printing a component with different materials, which is quite interesting to me. So it's, you know, if you would have instead of a typical coated part or a coating on a part, where they can actually print the substrate right on with the printing material, change the alloys in the middle of the print.
Yeah.
So that has changed the whole thinking of traditional metallurgy. It's very fast. You can generate fast prototypes. I have customers that have a couple printing machines right next to their CNC machines, where I ask them, what do you do with that? Well, if a customer wants a quick prototype, they can download it from their CAD drawings, print it overnight, and take a part to the customer the very next day.
Wow.
So whether that goes into production or not, that's the question. But typically what I have seen in production are very, very high valued parts. A typical gear, for instance, would not be printed, not that I have seen so far. But a manifold for an actuator for a wing flap on an aircraft, fuel nozzles like GE Engine has done down in Cincinnati. They have warehouses full of printing machines mass producing thousands of fuel nozzles every day for the LEAP engine. And what that printed fuel nozzle does, it makes I think there's 18 fuel nozzles per LEAP engine. The printed geometry of that nozzle allows for better fuel flow into the engine, which basically saves fuel, billions of dollars of fuel. And it's very light. I'm not happy to say that we used to braze a lot of those fuel nozzles, vacuum braze some of them. And we do not do that anymore because additive manufacturing has taken over on this brand new LEAP engine. We still do some on older platforms, but not for the LEAP engine. But that's that when you look up the mother of all additive manufactured parts, the fuel nozzle by GE is it. It's fully manufacturable. It's a high value part, but it saves billions and billions of dollars in jet fuel. Lockheed is the other one that's leading the league in this. They understand the metallurgy better. The traditional metallurgy of wrought product, when you melt bar or ingot, you have a more homogeneous structure. We understand mechanical values of traditional metallurgy. Additive manufacturing metallurgy, though, is quite different. You have cast layers of different powders. So what's the mechanical properties longitudinally and transversely? What happens when you lose power like I did just now and you stop in the middle of the build and then you restart again? What happens to the area, that heat affected area? I'll tell you, we've done a part already where we had a severe crack in the middle of it. Well, they found out they did lose power in the middle of the build. So that's the kind of things that are not known with this process yet that they're trying to understand, but there's a lot of money going into trying to understand it. And I believe some OEMs have figured it out. They just are holding it very close to their vest and not divulging it to the outside world yet.
Well, I think when you look at the business of 3D printing, I think a couple of trends, I've been reading a lot about this and hearing some, watching some videos on it, but there's two big trends that aren't even metallurgically related that could impact heat treaters' opportunity to heat treat more or less metal in the future. And one is, you and I talked about this in the manufacturing world, is printing on demand. So a manufacturer, like you said, GE, instead of sending those nozzles out to be a bunch of them to be produced in mass and heat treated in mass, they'll have printers. And this could be good in the automotive industry. It could be good across many industries, but they basically have printers in a warehouse and they're printing parts on demand as opposed to stacking full of inventory in a warehouse. And the other one is, and on the consumer side, there's many consumers out there that can now buy 3D printers that will print action figures, toys, all kinds of stuff, all kinds of little items. So if you're a person that is heat treating the metal molds that makes the toys, that business could go away. So you need to be looking at what kind of things are consumers beginning to be able to heat treat themselves, because that's going to cause the demand for either the molds that make it or the part itself, if metal's included, to go away almost completely because they're printing it at the consumer level. So there's some trends out there that they're related to the business end, but not the metallurgy end, that could make your opportunities go up or down. Another one that I just read about is for everybody that's in the automotive world. The reason it's not as big in the automotive world as it is the aerospace world is because the two things key in automotive are mass production and speed. And as you said, they've not been able to take 3D printing to mass production and speed yet. But that's not to say it doesn't come somewhere down in the future. So I encourage anybody on this webcast in the automotive world, you need to be studying this stuff all the time to make sure that it doesn't, because every technology goes to a growth stage, then a mature stage. And you don't want 3D printing to grow mature in your world and it pass you by. The other thing that I read about not too long ago, a lot of people say, well, they're only 3D printing small parts. Well, you alluded to custom cars, Bob, but at the Con Expo show, which is all the big agriculture manufacturers, they're going to 3D print next month. I think it's in Austin, Texas. They're going to be 3D printing an entire excavating machine from the ground up, part by part, the big everything, the big things that pull dirt out of the earth. They're going to 3D print one of those from the ground up on site in front of everybody there. So they're perfecting the technology to produce big pieces of equipment with 3D printing, which could or could not be a big threat to the heat treating industry, depending on what part you're heat treating and how much. But it's just something how the technology is shifting as we go.
That piece of equipment, I contend, would be good enough for one scoop of dirt, and that's it. And then it's junk. So how are they going to get hardened parts, gearing, transmissions in that piece of excavating equipment that's properly heat treating and that's treated? And that's the real answer that we need to find out, because Dr. Ryan Orhoff at Oak Ridge National Labs recently printed a piece of 625 Inconel, only 3x5 plate of Inconel, and with with the use of energy in printing that deposit of build plate of 625 Inconel, he was able to flip the grains to spell the acronym DOE for Department of Energy. Now, if he flip grains like that using power, what can he do? Now he's basically heating and cooling layers upon layers. Can he control the heating and cooling? What we do as heat treaters, can he control that enough to form microstructures like a martensitic microstructure? That's the question that I have, and that's the question that we all have. They're not there yet, but they sure are working like this every day. So that is the threat, I believe, that's out there. The other threat to heat treaters is that these printing companies that make these printers, they're trying to sell a vacuum furnace with a printer. As a printer sold, they want to sell a vacuum furnace, so you have it all self-contained. That's a threat to commercial heat treaters alike.
Are they making their own vacuum furnace, or are they sourcing that?
Outsourcing.
Gotcha.
Yeah. So that is a real threat out there too. So
sure.
And they, like I said, they hold a lot of their technology close to their vest, because what's happening now, those printing companies are all selling. They're selling to GEs. They're selling to Carpenter. Carpenter just bought Purist down south of Pittsburgh. GE has bought a number of printing companies. So they're buying these printing companies up left and right to gain that technology, to get this leg on this technology. And it's still yet to be seen. As I took notes on Tim Roberts' talk at the MTI meeting, Tom, those at the MTI meeting talked about, the typical hype curve of he gave the example of cell phone technology. I was one of those that had that big battery pack with a Motorola cell phone.
That was a weapon, not a phone, Bob.
It was a weapon. And that was on the top of the hype curve with that technology. Well, now he showed where the cell phone technology came back to a level playing field, like a normal curve, where it's part of everybody's life. It's part of our bodies, our cell phones. And he gave very good evidence that additive manufacturing is on the downward side of that hype curve and coming into the normal arena. And it's something that we have to all think about.
Mm-hmm. So a question from Scott Wagner just popped up, Bob. So is there any metallurgical issues in the part where it meets the base plate? I think he's talking about the first part that you talked about.
Yeah, that's a good question. Typically, the parts that I've seen when they do the EDM cut to separate the part from the base plate, there is always material removal on the bottom base. So I would assume there is some kind of reaction layer or some kind of heat affected zone, because that base plate's acting like a big heat sink. So I would imagine they do clear off some of that material off that base plate, the surface adjacent to the base plate.
Awesome. Well, I was talking to someone the other day, and we were talking about disruptive technologies, and certainly 3D printing is a disruptive technology. But when you think about the self-driven car, I just read an article the other day about with the self-driven car, when it becomes a reality, it's going to create a vast demand, a higher demand for organ donors, because a lot of organs that are transplanted come from people that have accidents and pass on from that. And so when you can imagine there's already people on waiting lists, well, if there's much fewer accidents because of self-driven car technology, that makes that a big, the demand is even more now. So, but with 3D technology, they're actually perfecting technology that prints human organs. So as one is creating disruption in a market, 3D printing is turning around and saying, hey, but we have a viable option. So that it's going to be interesting to see. That's why I think 3D printing is so exciting, as well as it's creating threats to many for people like in the health arena for printing organs. I mean, imagine if there was never a waiting list for any organ for anybody in the health world. That's pretty exciting stuff to be thinking about. So it does present a lot of opportunities in that area.
Yeah, Tom, that's where I see, yes, Tom, I see medical device companies. I see a big inroad with additive manufacturing there, where they can now take an X-ray and send it across the country to a place like Sintering in Westchester, Pennsylvania. And if you need a plate for your head, let's say, they can take a CAT scan of your head. They can manufacture a titanium plate for your head exactly the size of your skull and transport it overnight back to the doctor the next day. And those kind of things are happening. Same thing with hips and knees. The medical device world is really looking at this. Again, very high valued parts, and where the cost is, far outweighs the advantages. The advantages far outweigh the cost on a lot of these high value parts and high value materials.
Well, with a little bit of luck, Bob, you and I might be playing in a golf tournament at 100 years of age with MTI.
I only hope so. I have our power back on, so maybe I will make 100.
That's great. So coming around the corner here, so I know you made some predictions on 3D printing and additive manufacturing recently. I mean, would you be open to sharing some of those?
Sure. Just don't hold me responsible.
No, you're good. You're good. There's a lot of grays here.
These are Bob Hill's prediction, only my prediction. So, yeah, I've made some predictions before, and I've added to this list because, as I said a year ago, I was not that excited about this arena at all in heat treating, but I can see every day I can walk down on the floor and I can see more and more printed parts here. So some of my predictions are there's going to be less raw materials and more near net parts, shaped parts will be heat treated. It's kind of an assumption that we all can make. I believe there's going to be changes to the brazing services, just like the fuel nozzle that we've already have seen. Also, I think there's going to be a change to the coating industry or thermal spray, where now you can print other layers, if you want, of other materials within the same build. I once again believe hipping will become more prevalent, or CT imaging. There has to be some kind of quality assurance that there's no inclusions or voids in that build that could cause problems down the road, like we can avoid with traditional metallurgy. Substrate layers could be printed. What's to say that we couldn't someday print a gear out of, let's say, 1018 in the core, 1018 steel with a substrate of 4340 on the gear tooth, that we just harden that substrate, the gear tooth, leaving that substrate ductile. So mixing and matching alloys within the same component, or maybe even a nitraloy 135 case on the very tip of the gear to give better wear resistance. So the whole thinking of traditional metallurgy goes away when you think about the possibilities with the all that you can do with printing. I believe vacuum furnace will outpace atmospheric furnaces, basically for this reason. When we did this part for Norsk Titanium, we could not have any alpha case on there. Although they're going to machine a lot of that, not a lot of it, a little bit away, much less than if it was a whole bar. But we cannot have any alpha case on that part. So the only furnace you can use to avoid oxygen contamination like that on the surface would be vacuum furnaces. I do agree that because the printers are relatively small in size, I have some very large vacuum furnaces here. We're not putting printed parts in those large vacuum furnaces. These are more for the small furnaces because they're limited to the printer size. I also will say I have found out in the last year that an all metal hot zone is more desirable in a lot of these reactive metals like titanium and zirconium than a graphite vacuum furnace hot zone. And certain microstructures may be obtainable without conventional heat treating, with the rapid cooling and power control capabilities of the manufacturing. So there's some of my predictions. Also, maybe down the road, our pricing structure for heat treaters will be totally different. But it's something that I'm seeing in my generation, I'm sure future generations are going to see a lot more of this type of work.
So Bob, you mentioned machining in there in a little bit ago. Do you see the machining world not going away, but seeing a large threat? I mean, when you print a part, does it need as much machining as it did before?
Like, a good question, Tom. This part here, all it really needs is be ground.
Right.
It doesn't have to be chipped away. It has the internal cavities. It has the basic shape. There still is machining or grinding still needed on the parts that we have heat treated. Machining is not going to go away. Not today. Maybe down.
But would it be lessened though? Is there less, or is it the same?
Oh, much less. So instead of hogging out a whole bar to this shape and having barrels and barrels full of very expensive titanium revert chip, now all you have is some grindings,
right,
from grinding the shape and cutting the base plate. Remember, they'll use this base plate again. It's going to be flat after heat treating, and they're going to use it again. But they'll utilize all just the basic part, that the basic shape that you see, and they'll have very little machining. So that's a big expense that they're saving in manufacturing.
So I got a big question. You know, back in the 80s and early 90s, turnkey manufacturing became the big buzzword. You get a manufacturer in there with you, and you basically try and help them develop, and you create from idea and give him the whole part. You think there's any avenues or opportunities for heat treaters to connect with manufacturers early on, and they help them develop the recipe and the paper drawing, and then the heat treaters then actually, instead of them buying the 3D printer and the vacuum furnace or whatever furnace they use, they're actually taking the drawing and developing it, and the heat treater is doing it from A to Z. You see any opportunities in that?
Yeah, that's currently happening now, Tom, with many heat treaters across the country. They're doing machining and heat treating.
Right.
This is the same principle. They would be printing and heat treating. So yes, it's definitely a possibility.
Awesome. So any final things that you have to say to the community out there as they've been listening?
No, I just wanted to thank Tom for this opportunity. I asked Tom if he could get somebody else that's also involved with additive manufacturing, because I know there's others out there, and I wanted to have this as a panel discussion, but I guess we couldn't find anybody else, right, Tom?
Yeah, I mean, with the person we were going to have could not make it, but we're glad you stepped in. But yeah, I'm sure there's others out there. You started the conversation. That's what I'm excited about, and we'll continue that conversation in future broadcasts.
I started the conversation a year ago, I think at a FNA or a heat treat show. I forget which one, but I was not a believer then, Tom. And today I am with this technology, and it's here, and it's coming at us at a fast pace, and there's no avoiding it. That's why
That's awesome. Well, two things I'd encourage all the members watching to do. You need to go periodically to a site called trendhunter.com, trendhunter.com. It's a group that specializes in showing behavioral trends, manufacturing trends, and almost every industry you can imagine. And they have their top 20 trends at the end of every year, and they do short little 5-minute videos for them. But it gives you a sense to see how things are moving and shaking and changing so fast. But it gives you what you need to know in order to make your decisions, what markets you want to be in, what markets you want to pull back. And the other one is just continue to read. I know, technically speaking, ASM puts out some great articles on 3D printing and additive manufacturing. MTI is working very hard to help you understand the business aspect and opportunities of 3D and additive manufacturing. So get as informed as you can on this. And what I'd like to say in closing is I'd like to thank everybody from coming. I know I saw one of our members out there, Bob, Norman Hansen from Edmonton, Canada, out in the middle of Canada. And it's so awesome to be able to touch him from the office here. I know we can't get that far, and he's had challenges getting the meeting. So I just want to say hi to Norm, see him on the show and stuff. But you will not want to miss Heat Treat Tuesday in May. It's going to be on May 30th. We're going to be hosting Ron Hetrick, who's the chief labor economist from the Allegis Group, the largest skilled staffing firm in the world. And we're going to be focusing in on everybody on this screen has a problem finding good people, because all the good people that are teachable, trainable, want to work, and have a good work ethic, they're all working. There's no more. And I'm sure there's some out there, but what he's going to show is where have all the people gone? and what's your prospects for finding good people over the next 7 to 8 years, as we have a shortage of quality people. Because I've traveled around and talked to many executives in the construction industry, the chemical industry, the attorneys, the CPAs, the eye doctors. There isn't an industry out there that isn't facing the same thing everybody on this webcast is facing with finding good people. Everybody's fighting for them. I'm excited to talk about next time about MTI's Educational Foundation giving 3 $2,500 scholarships this year, and we'll be giving more over the series of the next few years. Our new apprenticeship program that's coming out hopefully by the end of this year. So the combination of all that will give us a nice strategy in the heat treating world to pull in those younger generations into each of our member companies. So appreciate everybody for tuning in. And Bob, thank you very much. Wave to everybody and say bye. Thank you. We will see you on May 30th at Heat Treat Tuesday again. Thanks, everybody. Have a good day. And remember, you're not just strong, you're MTI strong.